Lucas. Thanks to the organizers for inviting me. Especially thanks to the organizers for inviting me, because I'm not really in quantum thermodynamics, strictly speaking. So as I said during the meeting yesterday, I'm an outsider in this field, very interested, very curious, but my contributions to the strictly speaking quantum thermodynamic field have been limited so far, and I'm going to tell you something about it. So first of all, I'm a professor at the University of Pavia in Italy, which is this old medieval town. University is one of the most ancient in the country. It dates back to 14th century, and you're welcome to visit, of course. Pavia is located about 20 kilometers south of Milano, so you can easily fly to Milano and then reach us. The reason why there is no title in the first slide is that the title that is announced for this workshop is our work on modeling an artificial neuron onto a quantum computer, onto a real quantum hardware, and that's what I'm going to present you in a couple of slides. But I thought I should advertise a little bit our contribution to, this is really related to quantum thermodynamics, our contribution to this field, which is a work that we did a couple of years ago with my PhD student, Francesco, and in collaboration with Alexia Ofev, that most of you know, and Marcelo, both co-organizers of this workshop. Actually, I thought initially that it would not have been appropriate to present this work because two of the organizers are co-authors, so I thought, okay, I can present something else, but I still want to give you a couple of hints, and if you're interested, we can actually discuss more extensively about it in the discussion sessions on Thursdays, for example. Let me acknowledge, regarding this work, this project of visiting researchers that Brazil had that allowed me to come here the last few years for 1 month per year, and the Parachi workshop, in which this work was really conceived and got to an end. So what is the point? Is to use thermal resources to generate entanglement instead of work. This generally can be framed into a series of work on autonomous quantum thermal machines, which are not exactly producing as a useful resource what we commonly call work, but they are producing something different, which is quantum mechanically interesting. And this resource can be, for example, the entanglement. The typical scheme that one considers is, for example, a pair of qubits, a bipartite quantum system, mutually interacting between them, and connected to hot and cold reservoirs, thus mimicking the most typical scheme of a machine, of a thermal machine. And now it is very well studied, it's been studied for a few years now, that if there is a flux, a heat flux establishing through this system, there will be a steady state generation of entanglement between the two qubits. This is a genuinely non-equilibrium generation of an entangled steady state, and most people have called it an autonomous quantum machine, quantum thermal machine. In particular, works from Nicholas Brunner's group, Jonathan Borbrask, and Armin Tavakoli more recently. The problem is that with just classical thermal resources, the amount of entanglement that you can generate is really limited. In principle, you could generate a significant amount of entanglement by having reservoirs with an infinite thermal gradient. So one of the two reservoirs, the hot one at an infinite temperature, and the other one at a zero temperature, ideally. So you could, in principle, generate this significant amount of entanglement, but it's an unusual situation. Even more unusually, though, we thought, what if we relax the constraint of having only positive temperature baths? And then we realized that you can actually frame all this problem in a very general way. Any bipartite quantum system can be thought of can be thought of being described from a level scheme, which is sort of a diamond, what we call the diamond, in which you have a ground state, an excited state, and symmetric and antisymmetric combinations of the two first manifold excited state. And now, in a general framework of a Maxter equation, in which you have incoherent pumping and incoherent losses, you can easily go into a regime in which effective temperatures are not bound to be positive. They can be negative. And this is, in quantum optical terms, is very well established, because any system in which you create population inversion, you can describe the system as being at an effective negative temperature. And so by simply relaxing this constraint, it is very much like having the two symmetric and antisymmetric state coupled to different thermal reservoirs, one with an effective temperature and the other with another effective temperature. And what we showed is that if 1/3 is the limiting value of the concurrence as a figure of merit for a bipartite entanglement, going to 1/3, strictly to 1/3, in the limit of infinite gradients between the two reservoirs, infinite thermal gradients, if you relax the constraint of being only at positive temperature, you can actually reach the limiting value of 0.5 concurrence. So I remind you that concurrence equal to 1 is for a maximally entangled quantum state, and concurrence equal to 0 is for a fully separable state. Why you never can reach in such an out of equilibrium system the ideal one for the concurrence, you might wonder. And the reason is that the system will never collapse entirely into one of these maximally entangled states, because we are in a driven dissipative scenario. So the best that you can do, and that's what we showed in the paper, is that you can have at most half of the population in the ground state and half of the population in one of the two, symmetric or antisymmetric, one of the two maximally entangled states. And this boils to the value of 1.5 for the maximal concurrence that you can reach. Now, to link with the thermodynamic of this problem, you can actually reframe it in a thermodynamic sense, and also motivated by the discussion that we were having yesterday on experiments that could be performed and the quantities that could be measured to effectively prove a quantum thermodynamic regime. What you can also show is that this mapping, where you have maximal concurrence for negative temperature in one of the baths and the positive temperature in the other, actually has a one-to-one correspondence with the rate of entropy production in steady state. If you calculate the entropy production in the steady state, you see that it becomes maximal exactly in the corners where this concurrence is maximized. So this is a very unusual thermal machine, if you want. It's a thermal machine which the resource, in this case entanglement, is maximized when the system works in a most irreversible regime, while conventional thermal machine work maximize their efficiency, so the production of work in the reversible regime. This works the other way around. And so we thought this is an interesting system, general scheme under which one can think of possible experiments. And the possible experiments are, of course, in the realm of quantum optics. What we show in the work is actually that you can realize exactly this scheme by having two quantum emitters coupled to the same cavity mode in a single resonator, and both the full system, the two quantum emitters are incoherently driven by these pi rates. Even if the two qubits are not directly coupled to each other, there is an effective coupling mediated by the cavity mode. So this full system describes exactly the simple general scheme that I was telling you before, and it will give the results that I was discussing. So you could reach, in principle, this regime of effective negative temperature for one of the two reservoirs, and this limiting value for the entanglement generation. Now, if the entanglement that you generate in this out of equilibrium scenario is going to be useful for something, this is another question that we are still thinking about. Okay, good. So sorry to have spent the first few minutes of the talk discussing something that was not in the program. The remainder of my time will be devoted to present you a work that we recently made in collaboration with my colleagues at the University of Pavia, in particular my PhD student Francesco, my colleague Daniele Baioni at the Department of Engineering, and my other colleague Chiara Macchiavello, who most of you might know, at the Department of Physics. So this is one of those examples in which people coming from different backgrounds are really hitting to a problem that requires different expertise. In particular, Daniele, who works at the Department of Engineering, suggested us the problem of modeling artificial neurons on a quantum computer. And then with Chiara, we devised the algorithmic procedure that I'm going to present. Let me, since this is a bit off topic from the conference, and it's also different from what I was telling before, we switch completely gear. Let me give you a couple of introductory slides. The purpose, the general picture in which we are moving is that of artificial neural networks, which are artificial networks constituted by nodes connected by links on different layers. So there will be some input layer, some intermediate layer, which are often is called the hidden layer, and an output layer. Each one of these nodes, you might think of it as being a single neuron in an artificial brain. And the network usually works in the so-called feed-forward configuration, which each layer feeds the next one, but there is no backpropagation. So this is the single unit is actually mimicking the functionality of a single neuron, meant as an entity which has a body and a certain series of actions which create the connections between the different layers. Now, in the simplest version of an artificial modeling of a real biological neuron, what people know since the 50s now is that the most elementary unit you can model is what is called a perceptron. A perceptron is basically a unit that performs a simple operation on a series of input values. It applies a series of weights of values and performs an operation which is basically a scalar product. If you think about the input values as being the elements of a vector, and the weights as being the elements of an equally dimensionality vector, the perceptron performs the scalar product between the two. And it gives an output, which under a certain threshold can be discriminated between 0 and 1. So the output of the perceptron is still a binary valued function. It doesn't, the real result of the scalar product doesn't need to be 0 or 1. It has a certain spread in values, but you can set a threshold, and the threshold will decide if the neuron is going to be activated or not activated, so effectively as giving as an output 0 or 1. So this very simple model is the basis for the more complicated and complex artificial neural networks that are used today in artificial intelligence. Believe it or not, of course, the more complicated the neuron can perform, the larger set of values you allow it. But in the simplest version, it can already perform simple classification tasks by only giving binary valued inputs and weight vectors. And that's what we are going to model. So the linear perceptron, just the single perceptron, the single elementary unit of a neural network, can already work as a binary classifier. In this respect, you might think that even a single neuron can distinguish between black or white objects or squares versus triangles. It can basically, learn how to trace a line between two different sets. Of course, everything has to be binary, so it can only classify in a linear way. Not very sophisticated, but it's already something that you can do with a single element of this neural network. If you put several elements and you build a real neural network in a feed-forward configuration, this object can already do what now is evolving into the field of artificial intelligence. So the first tasks that the artificial neural networks can do are image and speech recognition, pattern classifications, and then more evolving more and more into deeper and deeper networks. This is going into translating, controlling vehicles, as you might have heard, learning how to play games, specific games like chess or Go, for example. And they learn this thing after having been trained for a certain number of iterations in the best way as compared to any human being. So this is quite amazing. Now, it's been already a few years that the field of artificial neural networks is converging with quantum theory. In what is called now quantum neural network models. Most of these, I would say most of the groundbreaking results in this field have been provided by people like Seth Lloyd, Rebentrost, Maria Schuld, who actually was a PhD student of Francesco Petruccione. So Francesco Petruccione is heavily involved in this type of research. And the general idea is on the concept of exploiting quantum mechanics to let these artificial neural networks perform their tasks in a more efficient way. And in this respect, let me distinguish between two broad classes of topics and problems in the field. One is trying to use quantum algorithms, quantum mechanics, to process classical information, and that's the subject of what I'm going to tell you. Another very interesting problem might be in the future to use these concepts to, for example, analyze and recognize quantum states. So that would be a quantum neural network modeling applied to quantum mechanics directly. The general concept is, of course, to exploit the superposition and the entanglement in a quantum processor to process information in a more efficient way, not necessarily much faster, but certainly more efficiently. And the key concept is that so far, most of the algorithms that had been presented were substantially difficult to be really implemented on existing devices. So what we did was basically to exploit quantum mechanics for what it's been, for what it performs better, so doing linear algebra. The key function is a scalar product between an input and a weight vector, as I was saying. So to perform this scalar product, you have to encode suitably the input and weight vectors on a quantum hardware. Our idea was that most people make the connection, the translation, a single qubit, a single neural node, as most of you might have intuitively thought about. We said instead, let's exploit the exponential scaling of the Hilbert space, and instead of encoding of making the connection a single node with a single qubit, let's encode the weights into the computational basis. So again, in the simplest version that I'm going to talk about, these values, these entries of the input and weight vectors are binary values. This is called in the field McCulloch and Pitts neuron. It's a perceptron, binary valued perceptron, if you want. And so the idea is that these inputs and weights are just the coefficients of the computational basis of a 2 to the power n of an hardware made of n qubits, which has 2 to the power n computational states. The algorithm that we devised is basically to calculate the scalar product of these two quantum states, quantum states with 2 to the power n elements, and by doing we did that by exploiting a register in which the encoding qubits on which the encoding qubits are performed through unitary operations, and we read the state of an ancilla qubit. There are two unitary operations that are applied. The first one brings the idle state, so the computational basis into the 0 state for all the qubits, into the psi state, so into the state that encodes the weights into the coefficients of the computational basis states. So this is the unitary UI. And the unitary UW is the operation that applied on the CW state, so on the state in which the weight vectors elements are encoded as coefficients, transforms this state into the state with all the qubits in the one. And then, so basically, by doing this transformation and the multi-controlled NOT operation on the ancilla qubit, you go from this state into this state in which the last element has a coefficient just corresponding to the scalar product between psi and psiw. So this looks very complicated, but it's extremely simple if you think of this state in terms of vectors in a Hilbert space. Let me give you a vectorial representation. You have this psiw state, and you have this psi. So the scalar product would correspond to the projection of psi onto psiw into the Hilbert space generated by the computational basis of the quantum hardware. The UW transformation basically rotates the reference frame in such a way that the psiw state is along the 1111 computational basis state. And so now if you measure on the ancilla the projection, the coefficient of the ancilla on this state, you are going actually to measure exactly the scalar product between psi and psiw. Of course, when you do that, you do it with a certain probability. And so this probability, the modulus squared of this coefficient, is the nonlinear activation function that we need to activate the neuron. A very simple example that you can do on your laptop, actually probably also on your smartphone, is to do it for just 2 qubits. 2 qubits would encode 2 to the power 2, so only 4 elements vectors in the input and weights. This is basically can discriminate. If you think of the plus minus 1 as encoding white or black, this can basically classify checkerboard or horizontal and vertical lines. This is the very elementary thing that you can do. Now, if you apply to an input vector which has this encoding a weight vector which is exactly the same encoding, you're going to get a product of 1. So it means that the neuron recognizes the input if it applies this weight. If you do the same for the negative pattern, you're going to get exactly the same result. So since the modulus square of the amplitude that you're going to measure on the ancilla does not distinguish between positive and negative, this neuron is actually able to classify positive and negative patterns on an equal footing. But of course, if you're going to apply a weight vector which is orthogonal to the input one, you're going to get 0. So in this case, the neuron does not recognize the input vector. Now, for the case of 2 qubits and a 16-dimensional, a 4-dimensional input and weight vectors, you can actually perform this for all the possible 16 combination of input and weight vectors. And this is the mapping that you're going to get. This is the exact result for 2 qubits. The neuron, this is the scalar product, which is 1 every time the weight vector exactly coincides with the input vector. And there is a symmetry, of course, because it, as I told you, it does not distinguish between positive and negative patterns. And all the other values are suppressed. We did the experiment of this modeling of an artificial neuron directly on the IBM quantum processor. For this experiment, we used on cloud, we used the 5 qubits quantum processor, which has this topology, in which 2 of the qubits represent the neuron, and a 3rd qubit is used as an ancilla. And as you see, the measured pattern is very, very similar to what was ideally expected. Now, this is non-trivial because it requires a certain depth of the quantum circuit. And we were pretty happy with this result. of course, there is a quantitative discrepancy, but if you think about the threshold discriminating between what is recognized and what is not recognized, if you put a threshold at 0.5, this neuron would recognize it in the 100% of cases. I'm going fast now. This is a detail, but we could only implement this result on the real quantum hardware because Chiara Machiavello is an expert of hypergraph states. And these type of states, which are called really equally weighted states, are actually isomorphic to the hypergraph states. This allowed us to actually implement the algorithmic procedure to generate these states in a much more efficient way. If you do it brute force, the quantum hardware would perform much, much worse. The most exciting part, sorry if I take another couple of minutes, is the training. We, of course, wanted to train the artificial neuron by giving a certain training set and letting it learn, for example, how to recognize a targeted vector. For doing that, we, of course, did it for a larger Hilbert space, like 16 input vectors, which requires 4 qubits to be implemented, plus 1 ancilla. And this is not possible to be simulated on the real hardware, so we had to simulate only theoretically. And this works very well, actually. So the single neuron implemented on a 4 qubits ideal processor for the moment is able to recognize a cross after a few steps with a training set which is only a few percent fraction of the full possible states. This is a single trajectory, and this is the average trajectory which converges to the targeted outcome. So recognizing a cross or its negative, as I reminded you. Very nice. So just to give it a perspective in terms of thermodynamics, what is really interesting now is to work out the information costs for these training rules. What I mean? What I showed you is that you can train an artificial neuron by having a certain training set, giving it an input, and after the neuron applies the rule to a given training set, it should be able to recognize a targeted vector even if the input is unknown. In this work from Seifert, they have shown by using stochastic thermodynamics tools that there is a bound to the amount of information that a single neuron like this can learn from a given training set. And this bound is given by the thermodynamic costs of the training process itself. What is now interesting for us as an extension of what we did, and this we are exploring in collaboration with Alexia, is to apply these concepts to a quantum model of the artificial neuron. How does this thermodynamic bound consideration change if we do it in a quantum setting? So let me summarize very briefly and actually acknowledge the IBM Q with this caveat that they, since we did it ourselves, they do not, our work does not reflect their official policy, but this is just politics from IBM perspective. Thank you for your attention.
Thank you for the nice talk. Questions?
I'm not expecting any question because it's really far from the topic of this conference. So you are free not to ask any question or ask me privately if you are interested.